Right, Stephen, we wanted to take a closer look at an event that happened last week because the week before Thanksgiving is always super busy. This year, it seemed like there were tons of conferences, but one of the biggest was Supercomputing. And Supercomputing 24 took place in Atlanta and had over 17,000 attendees and over 500 presenting companies. There was a lot of technology to discuss, and I think we wanted to jump in to a few of the announcements because I thought it was kind of interesting. But one I actually want to start off with was the National Science Foundation keynote, because I know that one of the largest consumers of supercomputing power out there is NSF, and they do a lot with it that maybe not isn't it's not commercially facing, but I think a lot of what they're doing to drive innovation in supercomputing kind of trickles down into the enterprise. So, what did you think about the NSF keynote?
Well, the interesting aspect really was, well, two things. Number one, that it focused on AI at an HPC conference. And number two, that it focused on the question of trustworthy, safe, secure computing. Now, really, there was two things that stood out to me about the NSF keynote. Now, number one, that it was focused on AI at an HPC conference, which may not surprise some of you who aren't intimately familiar with HPC, but generally speaking, the HPC community has been somewhat reluctant to be lumped in with the AI world. The other thing that surprised many was that it was focused on safe and secure and trustworthy computing. Now, that shouldn't be a surprise considering that it was given by Tess DeBlanc Knowles, who is a special assistant to the Director for Artificial Intelligence at the NSF and an advisor on the White House Office of Science and Technology Policy, co chairing the National AI Research Resource Task Force. In other words, she is one of the people who is responsible for developing and championing the current administration's approach to computing. And that means a heavy focus on trustworthy, safe, and secure and responsible AI development. Now, this is really an interesting aspect here because in the past, HPC focus as an industry has been basically let's see how fast we can go. Let's do this thing. Step on the gas, let's move. That's not exactly what's happening anymore. I think that the trend of, or the concerns over power consumption, over the proliferation of AI and AI technologies, and the ever rising costs of supercomputing are finally coming home to roost in the industry to the point where people in the industry are starting to ask questions about where they're going and what's rational and what they need to do in order to drive the overall HPC space forward. Now, I think that's a welcome change. I think it's a good thing that this is happening. But at the same time, you turn around, you look at the show floor, and there's a lot of the same. We are seeing, massive power sucking GPUs. We're seeing a proliferation of liquid cooling. We're seeing a lot of announcements around storage and networking. And frankly, that's where a lot of the buzz was. So let's take a look at a few of those things. Tom, I wonder if you can give us a look at some of the networking innovations that appeared at Supercomputing.
Yeah, probably the craziest one was NVIDIA's new Connect X8 Super NIC. We're going to link to a story from Serve the Home in the show notes. Go check this thing out. It is the most boring looking, amazing NIC you've ever seen. First of all, it looks like something that Big Bird would have in a PC. It is a big yellow heatsink stuck on top of this network card. In fact, Serve the Home says that this doesn't even look like a network card anymore. This looks like a GPU that has network connectivity. By the way, I want everybody to notice that is a single port 800 gigabit NIC. Single port with a giant heatsink. That should give you an idea of what kind of power we're dealing with here. But more importantly, it requires a Gen 6 X16 port. If you don't have one of those, you need two Gen 5 X16 ports in order to be able to run this NIC at full capacity. And I agree with the reviewer here. You have finally built a NIC that a CPU can't overrun. Like, that's impressive when you think about it. Like, think about all of the problems that you've had in a system. I liken it to like the interstate highway system, right? Like when we fix a bottleneck, we don't actually fix the traffic problem. We just move the bottleneck to a different area, right? So when we make memory faster, then we move the bottleneck to the CPU. When we make the CPUs faster, we move the bottleneck over to the storage. Historically, though, if you're doing things in and out of a computer, the bottleneck has always been the NIC because there's only so much data that I can force out of that pipe. But for NVIDIA, they're trying to eliminate that. 800 gigabit per second NICs. I remember when I first got involved in, like, doing networking and on social media, and I thought how amazing it was that we finally had a 400 gigabit per second spec. Like, we didn't even have hardware yet. It had just been finalized, and that was what, 12, 13 years ago. And now we have 800 gigabit per second NICs in production with giant heat sinks that look like video cards that can overwhelm CPUs with the amount of data that they can throw out. And NVIDIA is going to take full advantage of this with NVLink and all the other stuff that they're doing to be able to push data through these AI clusters as fast as possible. I think that NVIDIA is not going to stop. They have the CPU and GPU resources necessary to consume all of that data that's being thrown over that bandwidth. I think the biggest question that I'm going to have is, when is this technology going to be miniaturized and shrunk down and put into a form factor that would allow for more of these things to be plugged into a system? Because one of the biggest challenges, as we mentioned, is heat. And you kind of mentioned it in the intro, Stephen, but there are some solutions out there that are looking at going away from air cooling to liquid cooling. I mean, Flex acquired JetCool. Valvoline is showing off F1 inspired cooling tech. Are we about to switch away from blowing air all over these things to basically creating plumbed pipes to be able to keep things cool?
Yeah, it's all about liquid cooling, man, and that's what everyone was talking about from supercomputing was. Honestly, last year and the year before as well, obviously there was a lot of liquid cooling, a lot of immersion cooling, and things like that. This year, I talked to one friend of mine in the industry who went to a lot of these booths and saw a lot of these things, and essentially he said it's all about liquid cooling. We've gotten to the point now where air isn't going to cut it. Everything is liquid cooled. Everything interesting is liquid cooled, and it's everywhere. As you mentioned, we even have Valvoline, the petrochemical company here, talking about liquid cooling, advanced liquid cooling fluids. Who would have had Valvoline on their bingo card from a high performance computing show a couple of years ago? But here they are, and here we are. And it's obvious in some of the other announcements too. One of the things that was shown, for example, was NVIDIA showing off their GB200 NVL4. Now, again, this is not as necessarily a liquid-cooled platform, but it's a low-powered platform. So that's the interesting thing. So whereas you get these incredible news stories about the NVL72 and even the NVL36, which have just huge power requirements. This is a little boy. This is a little guy for smaller deployments, but for perspective, it's still 6 kilowatts. That's what we're looking at here. We're looking at the little, not even the little brother, the little baby brother of NVIDIA's latest Grace Blackwell combination. And it's still a 6 kilowatt package in a server with NIC and SSDs and other components. That's just wild, absolutely wild that we've gotten to that point where that's considered small and low powered. And remember, these things use ARM CPUs, which are lower powered as well. They've got integrated interconnects, which reduce the power consumption. A lot of work has been done to make these things more energy efficient, and yet we're still pulling down many, many kilowatts, even for a small platform. Another thing that we've seen as well is an increasing focus on utilization of processors and technology. That has been a big problem in the industry because if you've spent literally billions of dollars on expensive, high-end, latest generation NVIDIA GPUs and all of the stuff used to support that, and you can't keep those GPUs fed, well, then you've got problems, real financial problems. And that's where the storage industry is stepping up. So we're seeing companies like Hammerspace coming in with tier 0 storage that's much, much faster. We've got, Hitachi Vantara there. I was just talking to Weka about how they're feeding GPUs and that they're seeing this as one of the big markets for their Weka pod infrastructure. In fact, they just announced a high performance Weka pod that is able to serve GPUs even faster. Quantum was there with Myriad. Another product I want to call out, Solidigm. They just announced in New York a 122 terabyte SSD. That's a single device. Now, it's not something you're going to put in your laptop, but for data center and HPC usage, 122 terabytes. The news there is that the thing has unlimited longevity. Essentially, Solidigm guarantees it will work for 5 years, and it's incredibly fast. So, again, it's all about keeping those GPU pipelines fed. And that's where we're seeing in the storage industry. We've got vast data. We've got Panasys is now called Vidura, IBM, Dell, NetApp, Pure Storage. All these companies are in here talking about how they are able to keep these GPUs fed. And one of the things that I heard from an architect at one of the AI HPC companies was, quite frankly, storage is effectively free in the context of the amount of money it costs to have GPU resources idle. So they're willing to spend any amount of money to get absolutely not the best possible performance, but enough performance that those GPUs don't idle. And that is a massive opportunity for the storage industry. Any final thoughts, Tom?
Now, I think it's interesting that we've talked about how all of these rising tides have kind of lifted up. I mean, we didn't even talk about HP's Slingshot 400 switch, which is a 400 gigabit interconnect switch. It's needed to keep the AI HPC clusters running outside of those power hungry NICs and storage solutions. Like we've seen the acceleration of these pipelines significantly over the past couple of years because we're finally throwing enough stuff at them that we need that speed. I remember hearing all about how data gravity was going to cause all of these big data applications to live in these areas, and we were going to have to deploy the applications much more closely to where they live. And now, just years later, we're talking about, well, what if you could just stuff all of that data in a giant pipeline and shove it into these GPU accelerated Gen AI algorithms and do all this amazing stuff with it? It turns out that a lot of what we needed to do to innovate in the data center had nothing to do with making a slightly faster horse that eats a little less hay. We had to find a killer application that necessitated this. I mean, look at the number of times on the rundown this year we've talked about restarting nuclear power in the US in the next decade because it's the only way we're going to be able to feed all of these applications. Like liquid cooling, all of the components in the data center. I've even seen some talk about doing immersion cooling where we're just going to lay the racks over in a pool of oil. Like I don't even know. But then you look at things like AMD pulling ahead of NVIDIA in the new supercomputing list, and then like 72% of the new GPU power coming online is from AMD. I mean, what does that ultimately mean? It means that these companies are literally trying to outpace each other at breakneck speeds. And I don't know where the technology is finally going to fall over. And Gordon Moore is going to be like, you know what? I'm out. I've had enough of this.
Well, it's funny. We have actually pulled way ahead of Moore's law if you look at systems as a whole. Because of this parallel computing revolution, GPUs are coming online, dedicated AI processors are coming online. The absolutely brutal competition between Intel and AMD and ARM for the CPU space, between NVIDIA and AMD on the GPU space, and between many, many customers, including, of course, companies like Broadcom and Qualcomm on the neural processing space, it really has become a revolution. You look at, I mean, who would have had on their dance card that we would get to the point where we can't make these things run any faster in terms of gigahertz, and yet we're still doubling, tripling, quadrupling performance on a regular basis simply by adding more and more nodes, connecting them ever faster, feeding them ever faster. It really is remarkable where we've come with this stuff. And back to the beginning, it also raises the question that we have to think about the impact of what we have built here. We are building systems that consume just mind-boggling amounts of energy to the point where we have to span data centers. We're building systems that, as you said, require us to think about nuclear power and alternative power sources. We're going to have to figure out as an industry where we're going to go now that we've given ourselves this incredible gift of just massive, massive computing resources.